This is probably a little bit more complex than I'd like it to be, but we're going to work with it anyway. There is a wonderful term in chemistry called enthalpy. Now, enthalpy refers to the heat content. And we can see from this diagram here that the reactants have a certain amount of enthalpy, if I add them all up for the reactants. And in this case, the products have got a different amount of enthalpy. They've actually got less. Now, we have a huge problem. Enthalpy is one of those things that we can't actually measure. But we can measure the change. So this is what this stands for here. Delta is change. H was the letter. The chemists decide, capital H was the letter. Chemists decide to denote enthalpy. Right, so in a normal reaction, let's think about what happens. You can read the fine print later. We've got energy stored in bonds of my reactants. Now once I start the reaction, all the bonds are broken. So I get to a stage where I've just got single atoms up the top here. Nothing is bonded to anything. Nothing is bonded to anything else. All right? And then after that, we find that the new products form. So this means that these atoms rearrange themselves and are bonded in a different manner. Now the difference in heat content or enthalpy we can measure, and that's going to be the product or the basis of this little lesson. Right, so going through this again. In any chemical reaction, atoms are rearranged. You do not add or subtract atoms. We have the law of conservation of mass, which we've touched on before, which tells us that the number of atoms we have at the start and the number of atoms we have at the end must be the same. So if I have got 12 carbon atoms at the start, I must have 12 carbon atoms at the end. If I've got 5 nitrogen atoms at the start, I must have 5 nitrogen atoms at the end. Alright, so this is the basis also of our balancing equations activity we've already done. Alright, so we've got this one, so we're just going to rearrange them. And what actually happens is there is normally an energy loss by the chemicals. In other words, the energy involved in the products is less than the energy involved in the product energy. Oops, that's going to be confusing, but I'll leave it like that. So how about I fix it up a little bit? So if we sort of say, instead of P, let's use E for energy. Energy of products is going to be less than energy of reactants. That means the chemical has lost energy. In other words, the products need less energy than the reactants do. The alternative is if energy has to be put in, and the reverse applies. So in that case, energy of products have greater energy than energy of reactants. And I hope that makes sense. So what we're doing is looking at which one of them has got the most energy and then how much difference there is. That's what we're working on. Alright, so let's find out how we can do that. Now here it says the law of conservation of energy also applies. So not only have we got the law of conservation of mass, we've got the law of conservation of energy. So if you like, it boils down to the energy total, or the total energy we've got, will be equal to the energy in the chemical plus the energy in the surroundings. Now this is really, really important because what it allows us to do, we cannot measure this. Well, we have trouble measuring it. We've got trouble measuring this as well. Really lots of trouble. But we can measure this. And this is the joy of it. So this is what we're looking at. So we're looking at how this one changes, and that helps us out. Right, moving on. So remember these things. If we're going to try to measure it, we can't measure the energy in the chemical. So the enthalpy change is the difference between the energy in the reactants and products. So the delta H equals the difference in energy in reactants and products. And I hope that makes sense. But we can't actually measure that, but we can measure what happens to it, or the changes that occur on the way through. So let's see what we can do. If we put something around it, which we know lots about, for example, water, then we could see what happens to the water as the chemical reaction occurs. And this is what we do. This is how we measure enthalpy change. We look at what happens to the water in most cases that is surrounding the chemicals that are doing the reacting. So it becomes an interesting sort of an idea where we infer. In other words, we can't directly measure the chemical energies, so we look at the energy changes because by seeing what happens to what's going on around my chemicals, the surroundings. So one way we do it is do this. Let's say I'm going to dissolve something in here. If I know how much heat is in the water, in other words I measure its temperature, then I add the chemical to it and then I see this temperature change, I can deduce or infer what's going on. Now way back when, you learned a nice little thing about things called endothermic, which means heat goes in. Now, where does it go into? It enters the chemical. And of course, we have the opposite of that, which is exothermic. And this means that heat leaves the chemical. So if we look at those things and we then take it to the next stage, we can see that this really means that in an endothermic process, heat leaves the surroundings. So we can use what's going on with my water to tell what's going on with my chemicals. So the heat from the surroundings must be the same amount of heat that enters the chemical, because we had that equation before, remember it? E total equals E chemical plus E surroundings. So if that increases, that must decrease. That stays the same because of the law of conservation of energy. Easy can be easy. All right. Now, to try to stop heat leaving and to try to be as natural as possible, because we want to see what's going on with the water, we use a styrofoam cup because it will stop heat going through here and exiting. Okay, well, heat will go up here, so we could probably try to put a lid on, but that's another question. That's another story. So moving on, we can see that scientists have actually made a better go of this. And when we're actually doing it in real terms, what they do is they put water in a closed container, they add what they're going to test in here, and they use electricity to get it going. They measure the temperature of the water before the reaction, they measure the temperature of water after the reaction, they gently stir the water so that heat is the temperature of the whole water will be as consistent as possible. This, by the way, is called a bomb calorimeter. coming from the word calorie, and is simply designed to make this measurement occur. So all the values you see in data books, all the values we give you in class come from someone going to the trouble of testing a whole heap of chemicals in this way. And hopefully now we can see that calorimetry is really, really useful, and hopefully we can also understand how it helps us interpret energetically what goes on when something happens in chemistry.